in a little while. And she will probably also say a few more words about herself at that point. So the things we're going to try and do, if I can manage to get move my slides forward, is basically, well, two main things, and the third one, if there's time at the end. First one is basically answering or give a quick overview of what is this subglacial groundwater idea actually all about. So I'll do that part briefly without going into detail. Then Chloe is going to take over and going to show you why magnetotellurics in particular is very useful in this respect, which is maybe a question you've been asking yourselves. And then if there's time at the end, I'll say a few more words about whether it's possible, at least conceptually, to estimate geothermal heat flux from magnetotelluric data, which is coupled with groundwater flux and is obviously a variable we're all very interested in. Now, if we look at the big picture first, then here's a recent groundwater inventory from 2016, where you can basically see a lot of groundwater in dark blue, less groundwater in light blue, and where there's white areas, there's no information. And as you can see, especially in the high northern latitudes, there's no information on groundwater in these areas at all. And even worse, in the South, Antarctica doesn't even appear on this map at all. So there's clearly a big problem here that we need to address. Basically the headline poster here is that for contemporary ice sheets and glaciers, we fundamentally don't know whether there's groundwater beneath them. And if there is, does it actually affect the ice flow above it? We've been very lucky to have a few projects funded, which is, I guess one of the reasons why I'm giving this talk is something that we're going to really push in the next few years. So we have a big project actually dedicated to the groundwater idea on the Institute ice stream that's coming up in a couple of years. The project that Chloe will join us in as a postdoc on in Swansea is the GHOST project, which is part of the Thwaites Glacier collaboration, and which basically aims to detect, define, and quantify the basal boundary condition at the base of the Thwaites Glacier. And then Chloe will talk about an NSF project in the water, Helen Fricker, Matt Siegfried, Kerry Key, where they've already done some fantastic work on the Cyprus coast, and that Chloe will share with us shortly. But before we do this, I just thought I'll start very briefly in Iceland. You can see there's a sort of light blue coloring in Iceland here, which seems to suggest there's at least some groundwater here. So this is pool water depth equivalent in these colors. So there appears to be some groundwater there. And it turns out we're really not inventing the wheel here. And this is actually an idea that has been around for quite some time. For example, Gwen Flowers and colleagues had some naughty, fantastic papers in the mid-noughties here, where they modeled the basal hydrology and groundwater beneath the Vatnajökull ice cap and how they interact with each other, and then how they basically evolve over the next 200 years as the ice cap is projected to shrink. And it turns out that the flow patterns will change very substantially to the extent that they will affect the river basins basically around the Vatnajökull ice cap, and potentially can even isolate some of these river water basins. So this also has very important practical implications. And in fact, then if we delve deeper into the literature, it turns out there's actually a whole body of literature on the role of ice sheets in reorganizing groundwater flow systems. So this is something, for example, that Jeffrey Bolton's been working on since the 1980s. Many other colleagues have joined him in this quest. And I've just picked on this one example here out of many I could have chosen. There's many in Europe as well, for example, which is the Great Plains Aquifer System in basically Manitoba here, through North Dakota into South Dakota, which is the profile I'm going to show you shortly, which basically crosses the Williston Sedimentary Basin. If we pick a period in the Pleistocene where we have a growing ice sheet, then we have this sort of situation here, where we have high pressure water being generated at the base of the then ice sheet, which can potentially even collect in subglacial lakes. High pressure means the water is going to get pushed into the aquifer units, which you can see here in basically in white. separated by these confining units, which are shown in slightly darker colors. Yeah, basically you can see the groundwater flow patterns here, and then you can cause artesian features like the lake howe blowout structure here, for example. And then if I was interested to see how thick the sedimentary basin actually is, so in Wikipedia then tells me it's apparently 15,128 feet at the deepest point, and then the conversion in Google tells me that's 4,611.014 meters apparently. There we are. Now, then what happens is, over time, the ice sheet will shrink and eventually disappear altogether. And it turns out that the groundwater flow patterns actually reverse in that case, and the water essentially flows back to where it came from. And interestingly, one of the reasons that groundwater hydrologists started being interested in this is because there was something fishy going on with the chemical signature of the groundwater. But if they analyzed it, and there also seemed to be something fishy going on with the hydraulic gradients in some of the sedimentary basins, where the water seemed to behave in a way that it really shouldn't. And this is basically what kickstarted this idea that ice sheets can actually reorganize groundwater flow systems. The question then is, so how could this potentially work in more detail? And I deliberately say, how could this potentially, because these are all things that we still need to figure out in more detail. But one situation could be where we have an ice sheet advance in the Pleistocene here, high pressure water, we have high hydraulic heads. So wherever we have subglacial channels, we have high pressures, water is being pushed out into the aquifers beneath, potentially through till layers at the ice base that we're all very familiar with here. And then when the ice starts to shrink, a bit like Greenland and Antarctica at present, we have a shrinking ice cap. So we're more likely to have this situation where the hydraulic head becomes lower, we have low pressure channels, and the water flows back from the groundwater aquifer into the channels, and thereby the channels will basically play a central role in coupling the basal hydrological system with the groundwater system underneath it. And as it turns out, of course, in Antarctica, we've actually had the perfect conditions by which these interactions between the basal hydrological system and subglacial sedimentary basins kind of happened over many thousands of years. So, for example, Stuart Jamieson and colleagues produced this map a few years ago, which basically looked at the effect of basal sliding on basal erosion. And you can see wherever there's red colors, we have a lot of erosion, wherever there's yellow colors, maybe not quite so much. But we also know from various studies that colleagues have conducted that there's deep sedimentary basins in many parts of Antarctica, for example, in East Antarctica here. So there's not so much erosion happening because the ice flow is quite not so fast there at the moment. But in the past, there was geological conditions that meant these sedimentary basins could form. Then there's known basins beneath the Institute Möller system at the Cyprus coast, and also for Pine Island Glacier and Thwaites, we still need to figure out exactly how that works, and hopefully we can do that as part of our project. The reason I picked on those 4 examples here is because they actually feature a little bit later on in this presentation. And then, as Christine Dow had showed us in her yet another fantastic talk a few weeks ago, Stephen Livingston and colleagues basically reconstructed, and this is one reconstruction out of several, very active subglacial hydrology beneath much of Antarctica, including channels as well as distributed systems. And it's now up to observationalists to figure out ways of actually measuring these systems and ascertain what form they have. Okay, so there's plenty of evidence, as you can see, to ask this question: is the flow of Antarctic ice lubricated by groundwater that was basically built up when the ice sheet was advancing and is now flowing back towards the ice sheet base? And interestingly, so Paul Gustafson and colleagues basically pulled together a hydrological budget of the Cyprus coast ice streams, and the highlight of this is if we take the Camp, Mercer and Whillans ice streams together, then we find that around 47% of water flows in from the ice sheet interior, about 8% comes from local basal melting, and the rest was missing unless we allow groundwater to basically flow into the shrinking West Antarctic ice sheet from underneath. And as you can see in this budget calculations, there's about 45% of it, which is nearly half of the available water. So that's quite substantial. And likewise, so Brad Gooch, Don Blankenship, and Duncan Young and colleagues did some modeling for the East Antarctic sedimentary basins, where we can see the volume flux of groundwater across between the basal hydrological system and the groundwater system here on the left, negative downwards, positive upwards, over a glacial cycle, 20,000 years, depending on sediment permeability. And as you would intuitively expect, the higher the permeability in blue, the more flux we will get, and the lower the permeability, the less flow we will get. And the key point is that if the ice sheet is growing, the water will flow out of the ice sheet base into the groundwater system and recharge it, and then the situation will reverse when the ice sheet starts to shrink and the water flows back from the groundwater into the ice sheet base. In summary, really the headline importance is here really is that we can have a time lag between hydrological forcing and ice sheet response. There could be thousands of years, or potentially even more than 10,000 years, coupled with groundwater. And if there's time at the end, I'll say a few more words about this, is also geothermal heat flux that gets transported to the ice sheet base, particularly focused in these sedimentary basins. So the basins are also then conditioned for rebound when the ice unloads, so they're wet and they're warm, so they're very likely to relax as the ice unloads. And all this, of course, then is potentially, depending on how this turns out, a possible nightmare for ice sheet modelers. So I apologize for that. Okay, and so this is all well and good, and then you can ask yourself the question now, so what do we do about this? So what do we actually need to measure if we're trying to characterize this system? And so here I've picked on a reconstruction of the Pine Island Glacier from geophysical data presented by Atsu and colleagues a few years ago, where we have a few hundred meters of sediments here beneath the ice. And the sort of things, of course, we would typically do is we'd use things like airborne or ground-based radar to estimate or map the ice sheet thickness and to estimate the inglacial and subglacial thermal regimes. We can do things like seismic reflection imaging to delineate and characterize the physical properties of the subglacial till. If we're really lucky, we can also look at some tunnel valleys. And again, if there's time at the end, I'll say a few more words about this. And we can use other airborne methods like gravity magnetics, as well as passive seismic and potentially active source seismics to characterize the sedimentary basins themselves. But what is missing at this stage, of course, is the question of, is there liquid water in the sediments? Is there frozen water in them? And if so, where is it? And this is really where we need electromagnetic techniques. And this is the point we're at the moment, is where we're basically trying to figure out how to make good measurements and then how to interpret those. And then ultimately, once we're a little bit more confident with this, we can hopefully integrate all sorts of different types of geophysical data together with geological information to really be able to quantify the groundwater and geothermal heat fluxes. But this is maybe a few years down the line, but this is pretty much what we're going to be working towards. Okay, my final slide for now is this one. And again, just to demonstrate that we're not the first people that are thinking of this EM imaging idea. The Aarhus guys with their SkyTem system that are normally used to fly around Denmark and other places to measure groundwater systems went to the dry valleys and flew some fantastic surveys there. So here's the Canada Glacier up valley in this direction. To the left here, McMurdo Sound down there. So McMurdo Sound's here, up Glacier to the left. And what we can see is we've got very highly resistive ice. For Canada Glacier, for example, which is right here. Suze and Taylor glaciers further upstream. So tens of thousands of ohm meters here in resistivity. But if we look underneath these ice sheets or ice caps, we can see very, very low resistivity anomalies here of 10 ohm meters or potentially even less. And the only way we can explain those is we have like brine saturated sediments or essentially groundwater systems here in the dry valleys underneath them. So again, this is very encouraging to look at deeper systems, because the caveat with these sort of active source EM surveys is that they really only work very well if the ice is less than a kilometer or thereabouts thick. But when we get to much thicker than 1 kilometer, then we need to use other techniques like magnetotellurics. And at this stage, I'll let Chloe take over and tell us a little bit more about magnetotellurics and what we can do with that.
Great. Thank you, Bernd. I will start sharing my screen now and hit play. Okay, so I did just want to start by saying hi, I'm Chloe Gustafson. Thank you, Bernd, for asking me to jointly present this presentation with you. Right now, for everyone who maybe missed the intro, I'm at the Lamont Doherty Earth Observatory, but I'll be starting a postdoc with Bernd this fall as part of the International Thwaites Glacier collaboration. So to start, I did want to point out why methods like airborne EM and magnetotellurics, which I will talk about, are really useful for mapping groundwater systems, and in particular subglacial groundwater systems. So first of all, both of these methods are sensing electrical resistivity, which is an Earth property that spans several orders of magnitude. So here I'm showing conductivity, which is just the reciprocal of resistivity on a log scale, and plotted just some various resistivities for some different Earth materials. And the colors correspond to our conductivity and resistivity x-axis. So really what we can see here is that for various Earth materials, we're spanning almost we're spanning 5 orders of magnitude, which from a sensitivity point is a really good thing as far as being able to delineate these different geologic structures. And water in particularly, there we go, spans about 3 orders of magnitude. And this variation within water itself is a function of ion concentration. So if we have a lot of dissolved solids or salts, those can conduct electricity better, and therefore will have a greater electrical conductivity or a smaller resistivity. And when we're thinking about the subglacial environment, we're really thinking about water and also sediments. So we can start to differentiate between marine sediments and land sediments as well. And if they're saturated with water, basically we should be able to use EM methods to see how much water is contained within these sediments and how salty or fresh it is. And then in the subglacial environment, we also have ice, which is very resistive. So this creates a really nice electrical contrast between the ice and the underlying sediments that we're ultimately interested in for groundwater purposes. So like Bernd mentioned, airborne electromagnetic techniques are really great for subglacial imaging when the ice is maybe less than 500 meters. But as we start to get thicker and thicker ice, as we see for most of Antarctica, we do need to use ground-based methods in order to sense what's happening below the ice. So today I'm going to talk about magnetotelluric methods and why they are why this method is a good tool for doing this subglacial imaging beneath thicker ice. So magnetotellurics, or MT, is a passive geophysical method in which naturally induced source currents basically penetrate through this ice layer and into the underlying geology, and then generate secondary currents based on the conductivity structure that can be determined by fluid content. And then these secondary currents or electromagnetic fields then propagate back up to the surface, and we can measure those with electrodes and magnetometers. And this is really similar to just a physics 101 concept, Faraday's law. If we have a moving magnetic field going through some sort of conductive media, which in this case is a wire, will induce some secondary currents, which we can see the voltage changes as the magnet is going through the loop of wire. And this is basically what's happening on a much larger scale in my schematic here. So this is what it actually looks like to set up a magnetotelluric station. in the snow. We have this hub in the center, and then from there we spread out and bury our electrodes and magnetometers in the snow. And here I'll just show a quick time lapse of what it looks like to set up one of these stations. We typically leave these stations out for 24 hours for the purposes of imaging like the upper few kilometers of sediments. And if it's not too windy, then we can dig up the station the next day and move it to the next site. So here we had a team of 4 people setting up this station. And once we got into a good workflow, and if we had really good weather conditions like we did here, it takes about 30 minutes to set up one of these stations. So magnetotellurics is really great for imaging through thicker ice, but you can see it does take a bit longer to collect one sounding, a ground-based sounding, than it would to be to fly a helicopter over this area. So once we collect our electric and magnetic fields, we actually have a bit more work to do if we want to say something about subglacial hydrology. So first, we turn these electric and magnetic field measurements into a response function via time series analysis and applying our EM physics. And we generate these for each of our stations. And these give us a qualitative idea of kind of what's happening beneath the ice. But really, if we want to have a depth-based image of what's going on with the electrical resistivity, we need to perform geophysical inversion. So that gives us some sort of 2D cross-section of what the Earth might look like beneath our stations. And then the final step is to really take this resistivity model and turn it into something that is potentially a bit more useful or practical for other Earth scientists. And in this case, we're going to convert our images to groundwater salinity. And in order to do this, we need some sort of petrophysical relationship. Okay, so now getting to the actual data that we collected. Like Bernd mentioned, I'm going to talk about data that was collected on the Whillans Ice Plain, which is located on the Sipal Coast in West Antarctica. You can kind of see it on this little inset map. And this is work that I've done for my PhD, and I did want to acknowledge my collaborators, Carrie Key, who is my PhD advisor, also Matt Siegfried, and Helen Fricker. So here on this map, we're looking at the Whillans Ice Plain, which marks the convergence of the Mercer and Whillans ice streams. And this background shading that I've plotted on here is velocity, where the lighter blue colors represent faster velocities. Also, I've plotted these active subglacial lakes, which Helen discovered, and the satellite altimetry lines that she's used to determine that these lakes are changing in volume over monthly to yearly timescales. So here, warmer colors represent greater changes in these lake volumes. And also, we have these water flow paths shown in dark blue, and these show the predicted pathways between these lakes. And these ultimately, we think, bring water from the interior of the ice sheet through the lakes and out across the grounding line, shown in black, beneath the Ross ice shelf. And I've just noted that ice flow is in this general direction. So we completed 2 MT surveys in this region. Here we did one over Whillans Subglacial Lake, and then we also completed an MT survey where we think Whillans Lake eventually drains into the Ross Sea. So I'm going to start with our lake survey. Here again, I'm showing the ICESat outline with the predicted flow path, and ice is flowing from the top left to the bottom right. So I might be saying upstream and downstream. So this side of our survey is upstream and this side is downstream. Now our MT stations are these yellow triangles, and we were able to collect 27 stations over the course of 12 days. And these were spaced about 2 to 3 kilometers apart. And we designed this survey to be aligned with previous seismic imaging that has been done. And I've shown those lines in pink, and I've also highlighted in this darker blue color where the seismic imaging interpreted a water column to be present. And we've also aligned this with where the lake was directly accessed in 2013. So I will just start briefly showing these response functions for the stations that I've circled. I like to show these because we can see even before we perform geophysical inversion, we start to see variation in the data on its own. So here on the y-axis, we have apparent resistivity where the bottom is more conductive and the higher values are more resistive, and period on the x-axis, and basically the shorter periods are more sensitive to shallow structures like the ice, and the longer periods are sensitive to deeper structures like the underlying geology. So these are color-coded, the same on the map plot and here, and we can see that for our stations as we move across the lake and then off the lake, that we are seeing variation, especially for our off-lake site. It looks to be a lot more resistive at deeper depths. But let's look at an inversion model because that's a little easier to interpret. So when I take that data and perform 2D geophysical inversion, this is the model that I get. And again, I've circled the station so you can kind of orient where this image is relative to our lake. So here on the y-axis, we're showing about 5 kilometers below the ice surface, and on the x-axis, we're spanning about 15 kilometers. And our color scale here is log 10 electrical resistivity, where the blue colors are more conductive features and the yellow colors are more resistive. And really the main features that pop out to me are this deeper yellow resistive structure and this blue structure, which also has an even darker blue, more conductive region within it. So this is how I interpret this model. I have C1 and C2, which are my conductors, and together I think those represent the subglacial sediments that contain groundwater. And C2 is actually so conductive that there should be, or there needs to be salty groundwater in order to explain those high conductivities. And then beneath these sediments, we have R1, which I think is a low porosity sort of bedrock structure. And then here we can see that R1 is getting more shallow and the sediments thin, and our C2, our salty groundwater, kind of fades out a little bit. And you might be asking, why am I not including this bottom blue portion? And I will get to that momentarily. So if we take this to be the bottom of our sediments, that's about 1.4 kilometers worth of sediments, where the salty part of our sediments really starts. The saltiest parts begin around half a kilometer down. And then over here, the sediments thin out to about half a kilometer. And something that I don't really have time to get into, but I think is very interesting, is that where we see this R1 shallowing and the corresponding sediments thinning, this corresponds really well with our ISAT lake boundary over here. So I think there may be some story to tell about how these deeper, really long-term geologic features could be affecting short-term features such as subglacial lakes. So something to ponder. This is the model that I think is perhaps a bit more representative of what's happening. So this is now a more clear base to our sediments, or top of our low porosity zone. And here really, I've actually inverted the exact same data that I showed in the previous slide, but I've just allowed my inversion to have sharp gradients in the vertical direction. And part of the reason we didn't have this like sharp boundary in the previous inversion is because MT, just by nature of the physics, doesn't do a very good job of resolving the base of conductors. So if we let our inversion know that and say, hey, I want actually a really sharp boundary here, sometimes we can get nice models that look like this. So I think what we have are these thick sediments and salty sediments that are just sort of sitting at the bottom of the sediments. So this is all well and good, but now let's go ahead and take a look at our 3D grid of data. So here I'm actually just showing a bunch of 2D inversions stitched together, but we can see that there's really nice agreement across the whole lake. And really the first thing that pops out to me is that we do have extensive thick sediments that contain salty groundwater around beneath the lake and also in the surrounding areas. And here we're showing down about 4 kilometers beneath the ice base. And there are some general trends here. We see the sediments thinning in this downstream direction, and then also as we cross the lake left to right, there is some sediment thinning as well. So I think this image is really cool. It shows us that there are these thick sediments with salty groundwater, but here we are just showing electrical resistivity. And as I mentioned before, it's often advantageous to transform this into an earth property that perhaps might be more accessible for modelers to use. So in order to do that, the relationship that I'm going to use is Archie's law, which relates bulk resistivity, which is what we've imaged, to fluid resistivity, or this bulk resistivity is a function of fluid resistivity, porosity, and some cementation exponent, which describes how the grains sort of fit together. And in this case, we're interested in extracting the fluid resistivity because that maps very easily to salinity. So we have bulk resistivity taken care of, and we just need to take care of porosity and a cementation exponent. Now we don't have any deep subglacial drilling, so for porosity, I'm going to rely on drilling that occurred offshore in the Ross Sea, which is about 1,000 kilometers away from our survey site. And here I'm plotting that data, the porosity data as these black dots, and this is from IODP Expedition 374. And then I fit 2 different porosity decay models to this data with a preference of fitting this deeper data. So these are just 2 holes from this expedition with 2 different porosity models. And for M, typical values fall between 1.5 and 2.8. So in the next slide, I am going to convert this model into salinity for a few different values of M and also for these 2 different porosity decay terms. So here are our different potential salinity distributions. For each of these figures, I've plotted depth below base of ice on y-axis, and again, we have position on the x-axis. The colors here are log 10 salinity, and I'm using a unitless unit of salinity called the practical salinity scale, but it's really similar to parts per thousand. So for your reference, 35 on the practical salinity scale is about the salinity of seawater. So here we're plotting different porosity decay terms in the columns and then 3 different values of M being used for our resistivity salinity conversion in the rows. And I'm just gonna start by throwing out this top model because M equals 1.5 is more representative of sands. And in this sub-sea level marine basin, we're probably gonna expect muds and clay to be present. So M equals 2 and M equals 2.5 is actually probably more representative of what's really going on. So here I should highlight, I have in all of these plots plotted the seawater salinity contour in red and the brackish to saline contour in black. So we can see whichever model we choose here, assuming our Archie's transformation is representative of the subglacial environment, that we do have extensive saline groundwater beneath Lake Whillans. And this was actually predicted from the subglacial drilling. There they got pore water salinity measurements from the top 38 centimeters of their core. And this was predicted by Michaud and others that based on those pore water profiles that there must be some deeper solute source at depth. And that is what we're seeing here. So to make this just a little bit more digestible, I'm going to pull out some 1D salinity profiles from the upstream portion of the lake, and then this downstream, actually off the lake profile. And I'm going to do that for my least salty model and for my most salty model. So that's what those profiles look like. Here again, y-axis is depth below base of ice, and now our salinity scale is actually on the x-axis. And I've just colored these profiles using the same color scale on those previous plots. And the left line is the least salty scenario, and the right line is the most salty scenario. So I think these are the kind of, well, I hope these profiles would be somewhat useful as constraints or boundary conditions that hydrologic modelers could use. There's certainly some wiggle room in here. And in our salty profile, this actually looks like these salinities are a bit unrealistic. They're about 250 salinity, which is, we would have to have something really strange going on to get something that salty. Like for reference, the brines that have been observed in Dry Valley groundwater is closer to like 200. So I don't know if this is totally representative of what's happening, but this at least gives us some sort of bounds as to what some possibilities beneath Lake Whillans might be. And then we can compute some sort of seawater component. So these sorts of calculations will be dependent on the sediment thickness. So perhaps we could use these to better constrain hydrologic models. And then conversely, if we have deep subglacial drilling, we can actually use data from drilling to better constrain our EM models so that we can tighten up these bounds. So we know that Lake Whillans is underlain by extensive salty groundwater, and now I will just quickly hop to our grounding zone survey. And I'm just going to go straight into our 2D resistivity inversions. And I'll just note that again, we aligned our surveys with previous seismic and subglacial drilling surveys. So I'm using the same color scale that I used in my previous plots, so we can see the same features that I showed for Lake Whillans at the grounding zone. So we have our water saturated sediments that probably contain some fraction of salty groundwater. And I'll just quickly pull up one of those profiles, and I'll right off the bat note that this dashed section, we actually don't have the best resolution here due to a malfunctioning piece of equipment, but I think it's really likely that our C2 extends through this area. And one thing that I think is really cool, and I just wanted to briefly point out, is that even though we lost some resolution in the near surface, we do trust our deeper R1 structure here, and we see this fall off right here, which actually aligns really well with a fault that was identified with gravity surveying by Muto and others in 2013. So that's just plotted in black. And I did want to point out these sediments are about 1.2 kilometers thick. And perhaps over here we might be seeing another fault. And now I'm just going to pull out a 1D salinity profile from this region, which I think is sort of representative of this 2D profile for salinity. But to start, these are just our SLW, our lake, subglacial lake profiles, the least salty and most salty situation. And then I'm plotting the grounding zone salinities as these thinner lines. And I think this is really interesting because the grounding zone is actually, looks like it's less salty than subglacial Lake Whillans, which is not what I would have expected. I would expect the closer you are to the ocean, the sediments are going to be saltier. This could potentially be a function of sediment thickness. So those grounding zone sediments were a bit thinner. I think it's still something we need to think about. And another thing that is obvious when looking at these 1D plots together is that the point of maximum salinity is actually quite a bit shallower at the grounding zone than it is for Lake Whillans. So this is my vision of what's happening in the Whillans subglacial system. We have our ice stream that is flowing out towards the ocean, and plenty of research has shown us that this ice stream motion is modulated by this deforming till layer and also this basal water system. And with the data and results I showed you today, we also have these really thick sediment packages beneath our subglacial system, and these sediments contain groundwater, which gets saltier with depth and potentially less salty upstream from the grounding zone, at least looking at R2 profiles. But as I mentioned before, this could actually just be a function of sediment thickness. So my take-home message right now, at least, is that we have found extensive saline groundwater beneath an ice stream. And when we think about hydrologic modeling and the water systems that control ice flow, I don't think we can ignore these sediments. And Bernd sort of alluded to this earlier, is that this is potentially the nightmare for ice sheet modelers, but it's there and it needs to be included. And based on the paleohydrologic modeling that has been done in the Northern Hemisphere, I think that's just another line of evidence that this groundwater can be important for how ice is flowing. And the story certainly isn't over. We've seen that these sediments and groundwater systems are here, but there's still a lot more that I think we can use these for, or I guess we can use these to figure out other processes happening in the subglacial environment, such as alterations to geothermal heat flux, eye velocity, telling a story about ice sheet history and marine incursions. And also this groundwater is probably really important for the biogeochemical cycles that happen in these subglacial environments and are eventually transported out into the Southern Ocean. And with that, I will give it back to Bernd. And sorry it took a little longer than I thought I would.
Okay, thank you, Chloe. I'll try and quickly share my screen again. I think it's this one, hopefully. Yeah, so hopefully you can all see that. If not, then maybe Tavy can shout at me. So this is the last slide, obviously, that I'd finished on earlier. So just to spend I only have a couple more slides now, maybe 3 or so. So I'm not going to keep you very much longer. And again, if it gets too weary, then Tavy is going to have to tell me off. To just kind of bring home this message, when we have additional information, we can actually get much better EM images of the subsurface, and that also pertains to magnetotellurics. So, for example, we had an SEG paper in 2019. I don't take any credit for this, so Carrie Key did all the modeling for this. But in this case, we basically took Tom Jordan's geological template for the Institute ice stream here, Bungenstock ice rise, and we kind of conceptualized the sedimentary basin. We added some fictitious aquifers and aquithards to it, some tunnel valleys, subglacial lake here. And we wanted to see what happens is if we run unconstrained inversions like those that Chloe presented you with, or then if we assume we know all the boundaries from seismic surveys, from gravity or magnetics type surveys, then what would the difference be between those? And so here's an unconstrained situation like the one that Chloe showed you. You can sort of see that we can get a general idea of the features that we have conceptualized here. The bottom isn't very well resolved for the reasons that Chloe has already outlined. We can sort of see the permafrost a little bit. There's some indication of the tunnel valleys, but all this here, if we didn't know we had to put these in, we probably wouldn't be very confident that it wouldn't, this could just be noise or related to some other type of artifacts here in our surveys. But if we now allow for these boundaries to be known from seismic surveys or other information, then we can resolve, as you can see, our features very much better. And of course, reality probably doesn't work like this because there will be trouble with acquiring the data. There will be various types of noise. So in reality, even if we have constraints, we probably expect the reality to lie somewhere between these two here, but hopefully we can actually constrain our inverted images a lot better to get better structural images and also actual magnitudes of the bulk resistivities that we reconstruct. And then finally, is this idea of, is magnetotelluric data potentially useful for helping us constrain geothermal heat flux? Here's the latest kind of plots from 2020, Lösing et al., where they took the 3 most prominent geothermal heat flux models for Antarctica, plotted them on the same scale, and this brings out very nicely what we all know is that they don't agree very well with each other, and there's quite a lot of work to be done to figure out what the problem is. In the Lösing et al. Paper, that was a Bayesian study, a stochastic study to try and figure out the sensitivities of the different methods to different parameters and to get an idea of what might actually be causing these problems. And they, in their study, basically figured out that the Curie isotherm and heat production in the crust are the dominating parameters for the thermal calculations, and that the use of incorrect models or sparsely available data lead to unreliable results. And I guess that's pretty intuitive as well. So that's good to see. And the idea here is pretty much like I mentioned earlier, is that we should use different types of geophysical data with geological information in order to get better answers. And in this paper here, they actually demonstrate this for the Antarctic Peninsula very nicely. So if you're interested, do go and have a look at this. And so from an MT perspective then, again, we come back to Brad Gooch's study here, where he produced some very nice models for radioactive heat production in the crust and groundwater volume fluxes. And then we have the predicted vertical heat flow along here and elevation from the ice sheet base here. So the base of the ice is up here, the 400 meters down at this point here. But what we can clearly see is we get very different vertical heat flows, even if we exclude these extreme scenarios here. Even within this interior package here, we get very different vertical heat flows depending on the crustal heat production as well as the groundwater volume flows, which turn out to be in sedimentary basins really the key parameters when it comes to vertical heat flux. And the question then is, can magnetotellurics potentially allow us to constrain these a little bit better? And so it turns out that so below 200 degrees Celsius, the bulk resistivity is approximately linearly dependent on the temperature. And the reason this is the case is because the warmer the water is, or the warmer the pore space is, the more excited the ions are going to be, and the more easily they can basically move. And the more easily they can move, the more this will enhance the conductivity, which pertains both to the electrolytic conductivity as well as the surface conductivity along the interface between the matrix and the pore fluid itself. And the vertical heat flux is then dependent on the temperature change vertically, for example, through the sedimentary basins according to Fourier's law. And we've demonstrated this in this 2019 paper that we published last year. And so it turns out, so I've applied this here just by way of example to the Thwaites Glacier, where Dusty Schroeder and colleagues predicted very high geothermal heat fluxes, both on average of around about 114 milliwatts per cubic meters, square meters, excuse me, but potentially also exceeding 200 milliwatts per square meter in some instances. We know there are some heat sources nearby in West Antarctica, in this region, potentially that might be helping here. And so we can do some modeling by making assumptions over, so we can add a fictitious sedimentary basin beneath Thwaites Glacier of different thicknesses that we don't know yet whether it's there, whether we have drapes, whether we have basins, or whether we have a rougher bed where these might undulate. But nonetheless, for this exercise here, I've just assumed we have a sedimentary basin of different thicknesses. And I've also picked some thermal properties from the literature, for example, from Subglacial Lake Whillans, where there was a great paper published a few years ago, reconstructing the thermal conductivity and things like that, for example. And if we just throw all those into the model up here, and we basically try and figure out what the bulk resistivity ratio then would be between the bottom and the top of the sedimentary basin, by assuming that the ice sheet base is at 0 degree Celsius, or you could use -2 if you like, depending on the pressures, but it doesn't make too much of a difference. And then I've calculated different curves here, both for the temperature at the base of the sedimentary basin and the resistivity ratio that we would expect for this minimum average heat flux, and heat fluxes of 200 milliwatts per square meter. And so to give an example, if we had a 1 kilometer thick sedimentary basin, for example, we'd expect for a geothermal heat flux of 114 milliwatts per square meter, a resistivity ratio of about 0.4 between the top and the bottom of the sedimentary basin. And we would also expect a temperature at the base of the sedimentary basin of so around about 40 degrees Celsius or thereabouts. And then this changes. So the resistivity ratio gets less if the sedimentary basin is thinner, and it gets more when the sedimentary basin is thicker. And likewise, the temperature, the thicker the basin, the higher the basal temperature of the sedimentary basin is likely to be. Obviously, this is an extremely crude calculation here, but it's just basically, I wanted to show you this just for illustrative purposes as the sort of thing that we can potentially do. And as Chloe has shown, even in the unconstrained resistivity situation, we can get pretty good values for resistivity. So a bulk resistivity ratio change of 0.4 is something that we should be able to reconstruct from our images here. And then if we interpret that information together with all the other geological information, other geophysical information, taking knowledge about the salinity change into account, then we might hopefully be able to also say something about the geothermal heat flux in addition to, or together with all the other methods that we have. Or certainly MT does have great potential in this regard. And this is something that Chloe and I are hopefully going to work on a lot more once she's going to join us in Swansea, which we're all obviously very excited about. Okay, and then just a final couple of slides to say something about the seismic work. So both our GHOST project and the Institute Ice Stream project will involve the Arvi, Olaf Eisen, Korn Hofstede and colleagues doing some fantastic vibroseis work, and they have some great work where they showed really nicely resolved sediment reflectors, for example, like hundreds to thousands of meters basically below the ocean floor in this particular case. But they also have some other examples of this in land. So hopefully we can get pretty good ideas of what aquifer systems actually look like on the inside. And then coming back finally to this tunnel valley idea, there's a bunch of papers actually from deglaciated situations like this one here in northern Germany, where we have an aquifer system of aquitart and aquifers punctuated by tunnel valleys, and these show up really nicely, both the aquitart and aquifer layers, but also the tunnel valleys here in our seismic reflection data. You can see this is a few hundred meters deep. It's a couple of kilometers wide along the surface here. And actually, these aren't very different to some of the things that people have already measured beneath the ice. Like I've picked naturally one of our examples here from a few years ago from Greenland, where we have a hard bedrock upslope here. We have hard bedrock on the left here, but we find quite a lot of these sedimentary basins here filled with sloppy sediments that are a few hundred meters thick and a couple of kilometers wide. So on the scale of these basins, we're pretty much similar to the tunnel valleys that we had in the northern German situation here. So if we're doing some intelligent surveys, hopefully we might actually be able to find some tunnel valleys beneath our ice streams themselves as well. And as I'm saying this, my final point is watch the Greenland sediment space, because some of you who might have been following this will realize there's more papers coming out almost every year now doing seismic surveys of various kinds in Greenland, and every time we look, we find more sediment. So a lot of this stuff that we just told you about today might also ultimately apply in Greenland and might be a very useful tool there as well. Okay, and with that, I'll finish off by introducing the triple bang that we will be able to enjoy next year. From Samira, Sami, and Kier, who will join together to tell us about 3 different things that you can see on these slides here. Probably talked enough, so I will shut up now. I'll let you have a look at this, and I'll take any questions. So thank you very much for listening, and apologies for maybe running slightly over time, but given there was 2 of us, maybe that's excusable.
Thank you very much, Bernd. Might add that it's not actually next year, but next week, the seminar from... So, any questions from people in the audience? Some thanks and applause coming there. Anybody with a question?
Yeah, hi. I actually have a question. Thanks, Bernd and Chloe, for that really nice talk. Chloe, I'm actually really excited to meet you. I'm based in Swansea as well, so hopefully let's catch up soon. I was wondering, I'm not really familiar with MT surveys, but how do you decide, or how do you determine the offset between the MT stations when you plan the season? Like, would a smaller number of stations decrease the resolution you have in the vertical axis?
It wouldn't necessarily decrease your vertical resolution if you decided to space your stations further apart. It would decrease your lateral resolution. So in that example that I pulled out from the grounding zone, where we kind of had that blurred out feature where I had to draw those dashed lines, I think that kind of demonstrated that if you space your stations out closer to like 5 kilometers, you might not get as good of resolution in the near surface between your stations. So it kind of depends on what sort of depths you're interested in imaging that has some influence on your choice of station spacing.
Okay, thanks.